Today we're going to be talking about inverse relations. Some of them will be inverse functions, and we'll get to that. But what is an inverse? Inverse is often thought of when I flip something upside down or I switch things around to where they're backwards. And that's exactly what an inverse relation is. An inverse relation occurs when the x and the y coordinates of one relation are switched with the y and the x in the other relation. So as an example, if I had 4, -5 as a point on my original function or my original relation, if I were to find the inverse relation, that point would then coincide with -5, 4. So my x and my y switch places. Sometimes the inverse of a function creates another function, but that's not always true. If we look at the example here, we've got an original function, and it is a function because it passes the vertical line test, if you recall that. If we do the inverse function, this is what it would look like, and it no longer passes the vertical line test. However, if my original function passes what we call the horizontal line test, so instead of a vertical line, I now have a horizontal line, then that means my new function, my inverse function, will pass a vertical line test. So in this particular case, since it did not pass the horizontal line test, my inverse function is not going to pass the vertical line test. Because remember, the x and the y coordinates are going to be switched. So if I have multiple x values for the same y, that means I'm going to have multiple y values for the same x when I take the inverse. So what I would like you to do is take a look at these 4 graphs that are up on the board and determine which of these graphs are considered to be functions the way they are drawn. You can get with your shoulder partner, discuss this. I'll give you about 20 seconds to figure out which ones fall into the category of a function. All right, so this first graph here, if we were to draw vertical lines, it would pass the vertical line test. Therefore, that is indeed a function. If we go to the second graph and we look at vertical lines, there are several locations in which it does not pass the vertical line test. So that is not a function. This third graph, this oval shape, if we were to draw vertical lines, it would not pass a vertical line test, so therefore it is not a function. And then we look at this last graph, it does pass the vertical line test, so this last one here is a function. I want you to answer this question: which of the graphs would have inverses that are functions? And also know why you know. So if we look at this first graph, if we're going to look at one that the inverse is a function, then that function needs to pass the horizontal line test. And if we look through on this first graph, it does indeed pass a horizontal line test. Therefore, it would be considered an inverse that is a function. This one here, if we were to switch the x and the y's around, and I were to try to do a horizontal line test, this one passes the horizontal line test. Therefore, its inverse is going to be a function. If we take a look at this oval, it does not pass a horizontal line test. Therefore, it is not going to have an inverse that is a function. And finally, this last graph, if we were to draw horizontal lines, it would not pass the horizontal line test. Therefore, it is not going to have a function as its inverse. If a function has an inverse that is also a function, this is what we call a one-to-one function. And the reason for that is because each value of x has a y value that is unique. But if we were to put in a y, we would come up with only one x value, and that x value would also be unique. So these are termed as a one-to-one function. In a one-to-one function, if your domain has a domain of, let's say, D, and your range is R, then the inverse of that function, which is abbreviated by f to the negative 1 power x, but normally we just say the inverse of f, has a domain and a range that is switched. So what was your original range becomes your new domain for your inverse, and what was the original domain of your function becomes the range for your inverse. So let's just say we had f of x being equal to x over x plus 1. What would be the inverse? How would I find the inverse? Well, if we start off by graphing the original function, this is what the graph would look like. But how do we find the new function algebraically? Well, recall that an inverse switches your domain and your range, or your x and y values. So when we solve these things, what we're going to do is we're going to switch all my x's out for y's and all my y's out for x. You say, well, in the original function, there is no y. Well, remember, this f of x portion can be replaced with a y. So we have y is equal to x over x plus 1. If I rearrange and I make all my y's x's and all my x's y's, I would have x is equal to y over y plus 1. You say, well, that's great, but what do I do from this point on? Well, now, since when we graph, we normally have it as y equals something, we need to take this new function here and we need to rearrange it to solve for y. So what would we do first to solve for y? Well, I would try to clear the equation of fractions first. So if I multiply both sides of my equation by quantity y plus 1, I would get x times y plus 1 is equal to y. Now I can distribute, so this becomes xy plus x is equal to y. Now here's where a lot of students will make mistakes, at least until they start remembering things that they learned from Algebra 1 and Algebra 2. A lot of people at this point would say, well, I need to solve for y, so I need to divide everything by x to get rid of this x, y piece. No, that's not the way we do it. Let's go ahead and get all of our y's to one side first. So I'm going to subtract y from both sides, but I'm also going to go ahead and subtract x from both sides, because I want all my y's on one side, all my non-y terms on the other. And now, once again, some people try to divide by x to get the y all by itself, but you cannot do that. If you were to divide by x, yes, this would become a y, but this would become y over x. And so you still have an x combined with your y. So what do we do instead? We are going to factor out our y term. So now this becomes y times the quantity x minus 1 equal to a negative x. And now I can divide by my coefficient of y to get it by itself. So my coefficient of my y term is x minus 1. So dividing both sides of my equation by x minus 1 gives me y is equal to negative x over x minus 1. We could change that if we multiply by a negative 1 over a negative 1, which of course those negatives will cancel out, which means I'm really only multiplying by 1, which doesn't change my value at all, but it would change the way it looks. It would become x over 1 minus x. It does not matter which one of these you use, both will be acceptable answers. If we plug that into a calculator and we graph it, this is what my function would look like. So here I have my original function. If I take the inverse, I get something that looks like this. Now you may be thinking, well, it looks like you rotated it, but that's not exactly true, and we're going to discuss that. So many functions are a lot more complex than what we just did, and therefore an algebraic way is often much more complicated than what we just did as well. But you do want to follow algebraic concepts and rules as you're solving these, even if they get a little bit more complex. All it means is you're just going to have to take a little bit more care when doing the problem. As I mentioned when we looked at the graph, it did not look like it was simply rotated. There was more to it than that. And what ends up happening is that since we are switching our x and our y components, that is going to actually cause the graph to be reflected over a y equals x line. To show you this, here is a graph of a function. If I draw a y equals x line, which is going to go at a 45-degree angle through my graph, and if I were to put a mirror right there on that line and reflect it over, this is what I would get. And that is actually what the inverse function is going to look like. So we are not rotating when we do an inverse. We're not flipping something over in an inverse. What we are doing is we're reflecting it over the line of y equals x. This is why whenever we have a point, let's just say this point right here, which is at -1, 0 on my original, well, since the -1 and the 0 are going to swap places in my inverse, that would make it 0, -1. Well, if you look at 0, -1, we have a point on our inverse function. These two are corresponding points of the two functions. And if we do that, it ends up looking exactly like we have it on the board right now. And you may be wondering, how can I know that I've got an inverse function that is correct? So, Mr. Pletcher, you give me a function such as what we just did, and you say, find the inverse. And so I switch my x's and my y's. I rearrange my formula to solve for y. How do I know that I did not make a mistake? That is a great question, and there is a way to know for certainty that you did indeed get the inverse function. What we're going to do is a composition. So if it is indeed an inverse function, then that means if I take f composed of my inverse, it should give me a value of x as my output. But that's not where I need to stop. I also need to check to see if I take the inverse function and I make a composition using my original function, I should also get the value of x. It has to be x, not -x, not 1 over x, not x to the second power. It has to be simply an x. Let's use an example here. Let's say one function is x cubed plus 1, and I've determined that I think my inverse function is the cube root of x minus 1. Well, how do I know for certain that that is true? I'm going to do a composition. So I'm going to take my original function, f of x, and instead of my x term, I'm going to substitute in my g of x function. And so that makes it the cube root of x minus 1, quantity cubed, plus 1. Now, if I cube a cubed root, it basically undoes each other. So that leaves me just what my radicand is, which is this x minus 1 piece. So I have x minus 1 plus 1. Well, x minus 1 plus 1, then minus 1 and the plus 1 cancel each other out, and I'm left simply with x. So far, it seems as though I've got the right answer. But I have to do the second check. That means I need to take my g function and substitute in my f function for the x. So now I'm going to have the cubed root of x cubed plus 1 minus 1. If I simplify this down, I get the cubed root of x cubed. What is the cubed root of x cubed? It is simply x. So in both cases, I have my compositions working out to where both of them give me a final value of x. So this means that the cubed root of x minus 1 is the inverse function of x cubed plus 1. There are some non-one-to-one functions that are important, and you can find inverses of those functions that are also functions if you restrict the domain of the original. And I'll use this one as an example. Let's say we had x squared. X squared is a function, but it's not a one-to-one function because remember, it does not pass the horizontal line test, which means if I were to graph its inverse, it would look like this, which again, does not pass the vertical line test for a function. The inverse function is possible if we do restrict our original domain. In this particular case, all of these points right up here are representative of these points on my function. And therefore, in order to pass it, I would need to restrict my domain to where it does not have any negative values, because those negative values would cause repeat values of my y's when I graph it the inverse. So if our example, we restricted our domain to be 0 to infinity, then we would get an inverse function of x squared being the square root of x. And since I restricted my original domain to be just positive numbers or non-negative numbers, then this square root of x will accept any of the numbers that I have in my restricted domain. I would like you to take out your calculators and graph the square root of x plus 3. Now that you've done that, does this graph have an inverse function? So take a look at the graph and try to determine, does it have an inverse function? Right, the answer is yes, and the reason being is it passes a horizontal line test. Remember, in order to be a one-to-one function, it has to pass the vertical line test. In order to be a function, it has to pass the horizontal line test in order to be a one-to-one function, which means when we graph its inverse, it will also pass the vertical line test. Now, what is the domain and range of your original function? Your original function cannot accept any values that are less than -3, because that would make my square root have a radicand that is negative, and I can't take the square root of a negative value. So my domain is restricted to -3, including that value, all the way up to infinity. My range of my original, if you look at your graph, the range is going to be from 0 to infinity. So it doesn't have any negative values. Now, the next question is, what is the inverse? So I would like you to find the inverse function of the square root of x plus 3. So if you recall, when we need to find the inverse, we're going to switch our x's and our y's. So I went ahead, instead of making an f of x, I made it y is equal to the square root of x plus 3. And now I need to switch out my x's and my y's. So my y becomes an x, all my x's become y's, and that gives me x is equal to the square root of y plus 3. And now, in order to solve for my y, I'm going to have to square both sides, which is going to give me x squared is equal to y plus 3. And then to solve for y, I simply have to subtract 3. So my inverse of my graph should be y is equal to x squared minus 3. Now, what I would like you to do is, on your calculator, keep your y1 as this function, but go down and make y2 your inverse function. And we're going to graph them on the same graph. Now, if you'll notice on your graph, you do have two curves that are working. Both of them are functions. Your original is the square root here, and then your new inverse function looks almost like an exponential function, or maybe half of a parabola, which is actually what it is. But what are your restrictions on your new function? So this red one on the screen, what are the restrictions of that? Well, if you stated that your restrictions on your x are from 0 to infinity, and your restrictions on your y values, or your range, is -3 to infinity, you are correct. We could find that even by looking at our original domain and range. Remember, in our inverse, the domain and range are going to switch places as well. So what was our domain of -3 to infinity has now become our new range. And what was the range of our original function, 0 to infinity, is now become our domain, 0 to infinity. All right, so today what we learned is that inverse relations occur when your x and y coordinates of one relation are switched with the y and the x of the other relation. Sometimes the inverse of a function creates another function, but that's not always the case. If it is going to make another function, then it is going to pass the horizontal line test. If a function has an inverse that is also a function, we name that a one-to-one function. And if the one-to-one function has a domain of D and a range of R, then your inverse function is going to have a new domain of R in a range of D. We also learned that we can verify the inverse by doing compositions. So if I do f composed of my inverse, that should give me a value of x. And if I do inverse function composed of my original function, that should also give me a value of x. If the function is not one-to-one, we may put restrictions on our domain in order to make it a one-to-one function and allow it to be possible.